Section 7.3 is titled Repeating Decimals. So up to this point, the only decimal that we've had a name for was what? What name were we giving to our decimals? Terminating. And terminating meant that they ended, correct? So what we're going to encounter in this section is one way that a decimal can never end. And one way it can never end is it could repeat. When was it that we said that fractions could be written as terminating decimals? What was our condition upon that? Yeah, and it was after we reduced the fraction, right? Yeah. So this happens when a reduced fraction has only factors of 2 and or 5. So what if we can't do that? Well, if the fraction is an integer over an integer, remember integers are positive, negative whole numbers. Okay, integer over an integer, and does not terminate then it repeats. So there's sort of almost like, could I just said it repeats, and there's a disclaimer in here. The disclaimer is it has to be a fraction that has a certain form, okay? And what this is really doing is it's saying, okay, we're not talking about things like square root of 2 over something, okay? We're not talking about pi over 3. So those are not the kind of values we're talking about. We're talking about something that either it's written as an integer over an integer, or we can change it so that it would be an integer over an integer. So like the one on the board over here that's at 9 over 0.35 behind me, it's not an integer over an integer right now, right? Because the 0.35 is not an integer. But if I multiplied it by 100 on top and bottom, I could turn them into integers, right? And then I'd have 900 over 35. That'd be totally cool, or 9,000 over 35, or whatever I need on the board. I would be able to get it into this form. So if I'm able to get it into this form and it doesn't terminate, then it's going to repeat. So what we're going to do first is we're going to take a fraction and we're going to find the decimal representation for it when it does repeat. Okay? So we avoided doing this in section 1, I think it was, and we only did it for ones that didn't repeat. So this is 1 divided by 24. So in this section of material, and this is true for this entire chapter, you're doing division. You're welcome to check your division on a calculator, that's fine, but you're going to show me the division that you're going to do. You're going to write it out, long division, okay? And I promise you I'm not doing crazy long division like I've seen my daughter bring home, where they do something like, you know, divide by a 3-digit number. This isn't crazy. It's going to be small enough that it's going to be doable, okay? Not going to be cumbersome to do, I should say. Okay, I've put a whole bunch of zeros on here, probably more than I need, but I am going to need to put some zeros in here because 24 does not divide into 1, and it does not divide into 1, 0, or 10. It does not, I mean, it doesn't, so we need 2 zeros at the minimum in order for this to work. So how many times will 24 go into 100? 4. So we're going to put the 4 above the 0 in the value as though it were 100. So I'm going to put these decimals above here so the decimal carries up. And then we have 0 above the 1, we have a 0 above the first 0, and then we have a 4 above the second 0.
Why did we go ahead and add 2 more zeros?
What do you mean?
Like we had it as 24
Mm-hmm.
into 1,000, and then why did we add 2 more zeros?
You can put as many zeros as you need. I just put a bunch of zeros.
Okay.
So we're going to need several. I may have more on the screen right now than we end up needing, but we're going to need several. All right, so what is 4 times 24?
96.
It is 96. So we're going to line the 96 up here, and we're going to take essentially 100 minus 96, and what we're going to get? 4. And then I'm going to bring my 0 down. So now I've got 40. How many times does 24 go into 40? One time. 1 times 24 would be 24, and we subtract. So subtract this, what do I get? 16. And then I bring my 0 down. How many times will 24 go into 160?
6.
It is 6. What's 6 times 24? 144. And what happens when I subtract this? I get a 16 again. So if I were to carry another 0 down, I'd have the same 160 that I had in a previous step. It happens to be the previous, like the exact previous step, right? So if I did this again, I'd get another 6, and then I'd get another 6, and I'd get another 6. That 6 becomes the part that's the repeating part. So when we write our answer out, we're going to write out 0.0416, and it's the first time that the repeating part occurs that we list, and then we put the repeating bar above that. So this is our answer. Now, if the repeating parts do not occur on subsequent steps, like let's say, for instance, right here, instead of getting 160 right here, we got 40. So the repeating part went back up to here. All right? Well, if it did that and it went 40 and then 160 and then 40 and 160 every time I kept going, we'd actually have 2 things that are repeating, right? So you have to be careful that you're looking back to where the repeating part occurs and not just put a little repeating bar over the last number you found. That's not going to work usually. Okay? All right, there's some notation for this. We call this type of decimal a repeating decimal. The repeating block of digits is called the repeat end. So in the last problem, that was the 6. The repeat end was the 6. I already said this out loud, but it's actually in your notes. So when you don't do it, I can say, I actually put it in your notes. Note, I expect to see division when you convert these. Okay? So if you're working with kids and you're wanting them to show you division, you're not going to accept them using it on a calculator, at least not right off the bat, right? You're just not. And so I would like for you to see that you're comfortable enough with it that you can show me you can do it too. That's all. And I know you guys are capable of doing it, so you're just going to show it to me for this section, okay? All right, fabulous. So we're going to do another one. Find the division, the decimal representation. So I'm just going to pause. I'm going to let you guys do this one. Go ahead and write down what it should look like. When you get to the point where you believe you have the final answer, compare with a neighbor. Make sure that you guys agree and that your answers match. Did you guys check with a neighbor? Do they agree? Okay, what answer, Leah, I'm going to ask you, what answer did you get? Okay, did everybody have 0.29 repeating, and the 2 and the 9 repeat, right? Okay, did everybody check that? You weren't sure where to repeat on yours, probably.
Well, I got 0.2892.
Okay, so you probably have a division mistake in there somewhere. So let's double check everybody's division to make sure everybody's looks correct. So we're doing 99 into 29. And of course it doesn't go into 29, so I'm going to put a decimal point 0, and we're going to consider it as though it's the number 290. So how many times will 99 go into 290? 2 times. And what is 2 times 99? 198. Now I need 290 minus 198. 92. Okay. So we're going to bring a 0 down. Now I need 99 into 920. It is 9.
Oh,
Did you get that one? Okay. What is 9 times 99? 891. All right. And 920 minus 891? 29. So here's where the first repeat happens. And it happened 2 steps back. So if you aren't sure, feel comfortable, or putting the bars on top of things, you can do a couple more steps. And you very quickly will recognize that the first one up here, like if I continue this process, I'm going to put another 2. And if I do it another, that's fine.
So if I did it again, I would have gotten another 9.
Yes.
So you would have realized it's 29.
Exactly. So if you recognize it and don't have to do the work to see more steps of it, that's fine. But if you need to do a couple more steps, you will eventually see, okay, these are the numbers that repeat, because now I see them repeat. I mean, I've seen them. It goes 29 and then another 29. Oh, it's going to keep happening. 29, 29, 29. So, but the reason it's happening from sort of a looking at it in a forward instead of a backwards glancing is because the repeat's happening 2 apart. I'm having 2 numbers that are repeating because they're these repeat 29 is coming 2 steps apart. So this number repeats, and my answer to the question is 0.29 with both the numbers repeating. Please do not make me guess what the bar is on top of. I will be not a happy camper, and you're probably just going to get it wrong because you're making me guess. So make it very clear where that bar is supposed to be over and what it's not supposed to be over, okay? All right, we're going to go the other direction. So flip the paper over. What we're going to do now is we're going to start with the repeating decimal, and we're going to turn it back in to a fraction. Okay? This is the part that you may not have seen done quite as frequently as the ones we just did. So the first thing we're going to write down is we're going to write down our repeating decimal, and we're going to write n equals on the left. There's nothing special about n. You can use whatever you want, but n is what your book uses, so I'm going to use n. N equals 0.61. How many decimals are repeating here? 2. 2 decimals are repeating. That's important for the next step. You have to know how many decimals are repeating. Because my next step is I'm going to multiply both sides of this equation. It's an equation now because it's got an equal sign between it, right? I'm going to multiply both sides of this equation by a power of 10. Okay? The power of 10 depends on how many repeating decimals I have. So since I've got 2 repeating decimals, this would be 10 squared, or 100. 3 repeating decimals would be a 1 followed by 3 zeros, or 1,000. 1 repeating decimal would be 10. Okay, so the number I multiply by, write this down. The number I multiply by depends on how many repeating decimals I have. Power of 10. Okay, so this is 10 squared that we're going to multiply by, and the square is happening because I have 2 repeating decimals. Okay, and 10 squared is 100. So we are going to multiply both sides by the number 100. Okay, so I'm going to do the hard side. That's the left-hand side. It's 100n. The right-hand side, though, is weird. Right? I was joking when I said it was the hard side. I did the easy side. Okay. The right-hand side looks weird. I mean, what do you do when you multiply a repeating decimal by something? Well, think about it. I mean, what is the repeating decimal? What does it really mean? Well, it means I have 0.61, 61, 61, and it keeps going, right? So what's going to happen when I multiply this by 100? It's going to move the decimal place. And the number is going to end up giving me a 61 now. You got it. So I'm going to have now a 61, but then I'm still going to have the 61 repeating, because moving this decimal place does not change the fact that the numbers are still repeating. So far, so good? Okay. Here's the step that people sometimes mess up. Sometimes they mess that step up. Sometimes they mess the multiplying by 100 up. But this step they often mess up. What we're going to do is we're going to subtract, and it's always the same, so I'm not sure where the disconnect actually happens. We always do the same thing. We subtract n from the left, and we subtract what n equals from the right. What does n equal? 0.61 repeating. So the subtraction, it's not about what's repeating or not repeating. It's what does n equal. In order for equations to stay equal, you have to do the same thing to both sides. Well, I can do this because n and 0.61 are equal. So I've subtracted the same amount from both sides. Different forms, but they're the same thing. Okay? So, on the left, I get 99n. On the right, and this is why we multiplied by 100. We multiplied by 100 as opposed to, say, 10 or 1,000 because we want the repeating part to line up. Doesn't it? 6-1 lines up with 6-1. So what happens? Yeah, they cancel out. They subtract out to 0. So I'm still left with the 61 before the decimal point, but the 0.61 after the decimal point gets eliminated. No more repeating decimal. What do you think the last step's going to be? Divide by the 99. Yeah, you had the right idea. No worries. And if these don't simplify, we're done. If it does simplify, we would do a simplification, like divide them both by 3 or something like that if they're both divisible by 3. I don't think this one divides out any further. It doesn't. So this is 61 over 99. What in the world could you do to check and make sure this is right? You could do division. What could you do easier? You could grab your calculator, double check it, right? Just grab your calculator. I'd like for you to put in 61 divided by 99. Is it 0.61 repeating? So do you even need a back of the book to know you're right? Not on this one. You can check it yourself with your calculator. How is number 4 different than number 3? Only the 1 is repeating. Okay? So the first part of the problem starts out the same. N equals 0.61 with the 1 repeating bar on top of the 1, not on top of the 6 and the 1. What's the first difference then between what we do? We're just going to multiply by 10. Yeah, so we're going to multiply by 10 to the 1. And it's 1 because there's only 1 decimal repeating. Okay, so we're going to multiply by 10 on both sides. So like I said, the left-hand side, that's the hard side, 10n. What's going to happen on the right-hand side? And that's true. It will be 6.1 repeating. But I really want to write it with the repeating part in the same place that it was before. Yeah, because you see, the idea when what I'm about to do, I'll write it down here. Let me write what happens if I write it the other way. I'm about to subtract 0.61 repeating, like this. And the repeating lines are not lined up right now. It's awkward feeling, right? I want them to line up so that when they subtract, they just disappear from the problem entirely. And without them being lined up, that looks really messy. So if I write the repeating bar in the same location, right, this isn't how we would really write it if we were writing the end of a problem. But if we write them in the same location, then the subtraction of the 0.61 has the 1 bar lining up. And then on the left, we're going to, of course, subtract n.
Why is it a 1 there instead of a 0 then?
Because it's 1 repeating.
Oh, okay.
Yeah. Yep. So these subtract out. But I do still need 6.1 minus 0.6. So what is that? 5 point what? 5. And I have 9n on the left. What's our next step? Divide by 9. You got it. Now, you do not get to leave the answer as 5.5 over 9. Why not? Right. The directions actually tell us that we want this as a over b, where a and b are integers. I mean, we can get it that way, but it's not that way yet. So what would I need to do with 5.5 and 9 to actually turn it into integers?
Multiply both by 10.
You got it. Multiply both by 10. That's the easiest fix. So what does that become? 55 over 90. Do we get to leave it like that?
No, we need to reduce it.
We need to reduce it. So yeah, by 5 is a good number here. So we'll divide by 5. What do I get? 11 over 18. Check it. Grab your calculator. 11 divide by 18. Is it 0.61 with the 1 only repeating? It is. Okay, we're going to do one more. Okay, so I'm going to pause for about 2 minutes and give you a chance to get it started. You might finish it, you might not. And then we'll come back together and make sure everybody has the same thing. So write down the steps as you're recognizing them and see what happens.
I didn't make it very far.
Okay. Did you make it that far?
Yeah.
Oh, that's good. Is everybody good with that far? You wrote that down? What was your next step?
Multiply each side, or make it, yeah, I multiply each side by 10.
Multiply by 10. Does everybody agree 10 is the right number? Good. So you multiplied by 10. So on the left we get 10n. What's happening on the right? 9.9 repeating.
Okay, just figured that out like right before.
Okay, that's right. Is everybody good with that part now? Okay, so now you've got the first, and then the repeating part lines up with where the repeating part was before, right? That's valuable to us. It'll make the subtraction cleaner. Okay, so what's next then? Subtract n, and it's n from the left and what from the right? 0.9 repeating from the right. Again, it's not always just the repeating part that subtracts. Like on this one over here, I subtracted part of this that didn't repeat, right? The 6 did not repeat, and yet it still got subtracted. Because n is equal to 0.61 repeating, all of it. You can't just pick and choose the parts you want to subtract. But it is nice because when I subtract this, on the left I get 9n. What do I get on the right? Just 9. What do you do next? And what in the world do you find out? You just proved something that I'll bet if you went to the GC today and you talked to people, 2/3 of the people would tell you is not a true statement. You just proved that 0.9 repeating is equal to 1. Didn't you?
I mean, obviously.
Because like 1 divided by 1 is, you know what I mean? Because like that would,
Mm-hmm.
like that's like 1 over 1, but 1 divided
Yeah.
by 1 is 1, but not that.
0.9 repeating is another way of expressing the value for 1. It's just another way of expressing it.
Would it be because you rounded up?
It's not rounding. There's no rounding involved. They are equal. It's not a rounded value. Do you feel a little uncomfortable with that?
It's just like hard to make your brain like.
Wrap around it, I know. Yeah. Okay, so I wanted to show you that because the next problem has a 0.9 repeating in there. I mean, I kind of wanted to blow your mind in general anyway, but, you know, the next one does have a 0.9 repeating in it. So it's easier to do this problem if you recognize that 0.9 is actually this repeating, is actually the same as 1. So this question is actually telling us we want to find a decimal between 1 and 1.1. So what would you do to find a decimal between 1 and 1.1?
Add them and divide by 2.
You could. You could definitely add them and divide by 2. And that actually is how we would do part B anyway. That's the exact halfway point. So let's do that for B. And then we can talk about what other possibilities we have for part A. So if we add these and divide by 2, What do we get? What was it? 2.2 over 2. And what is that? I'm sorry, 2.1 over 2. And then what does that work out to being, like as a decimal?
2.1.
1.05. Yeah, 2.1 over 2, but then dividing by 2, the 2, yeah, gives us the 1.05. I think if you think about this as money, you're probably going to make a observation on part 1 that we didn't really need to actually do division, and your calculator was highly unnecessary. Because what does the number 1 look like? Well, it looks like a dollar bill. What does the number 1.1 look like? $1.10, right? $1 and a dime, $1.10, $1.02, some variation of those things. So what's in between having $1 and having $1.10? $1 and a nickel, $1.09, $1.04. You have all of those, right? So you have like 1 point, and that's just thinking about it in terms of money, right? So I restrict myself to having 2 decimal places when I'm talking about money. If I want to have 3 decimal places, I could do that too. But any of these would be sufficient here. Okay. So if you were working with a problem that asked something like this, and it said you want to find a value between 0.59 repeating and 0.7 or 0.62 or something like this, I don't know, whatever number it gave you, the easiest thing to recognize is that the 0.59 repeating is really the same thing as what? 0.6. It feels like it's because you're rounding. You're really not. It's all based on the exact same argument that 0.9 repeating is equal to 1. Okay? So there are other ways to think about this one. I think that's a nice way to think about it when you get those 9 repeatings on things. All right, one last question. Let's do a show of hands real quick before we even... If you had to decide, I like decimals better or like fractions better, who likes decimals better? Okay, does anybody like fractions better? A few of you. I like fractions better as well, actually. This question actually hits on the fact that there are times when fractions or decimals are easier to work with, and it's talking about that. So some addition problems are easier to compute with fractions and some are easier to compute with decimals. For example, 1/7 plus 5/7, that's easy, isn't it? But 1/7 as a decimal is the decimal 142857 repeating. And 5/7 as a decimal is 714285 repeating. So if you wanted to add one of those sets of values together, I don't know about you, but I'm going with fractions. Okay? But if you worked with the numbers, for example, 4/10 and 25/100, it's easier to add that in decimal form. Not that the fraction form on that one is terribly messy, but it's still easier to do in decimal form than to do 2/5 plus 1/4. So we're going to describe, and I'll let you guys just write things down, describe situations where you think it would be easier to work with fractions and ones when it would be easier to work with decimals. What makes it easier or harder to work with one or the other? Do you have an idea, Jamie?
Well, it'd be easier if the denominators are the same.
Yeah, I agree. So fractions are easy when the denominators are the same. Does everybody agree with that? Yeah, so that's definitely it. If we have common denominators, fractions are fabulous. What else?
When they're not the same, it'd be easier to work with decimals.
It might be easier to work with decimals, but what if I had 1/7 and 1/3? They're not the same, but they're very difficult to work with because I already see 1/7 as 142857 repeating.
You can, but it might be easier to find, like, to make the denominator the same.
Why? What about that would be easier than
They have
the
a
decimal
common
form?
Denominator, or not, they have a common factor.
Okay,
Like,
but
you can change them easily because we can't explain it. Like, you can change the denominator, you
I
can times them by
I think I'm asking a little different question than you're answering. My question is, why would the decimal form not be easy to work with?
Oh, okay.
Yeah. What about those particular decimals that I just gave you, the fractions for, would make them ugly? Huh? They're repeating. I mean, some things repeating aren't so bad, but I'm telling you what, I do not want this 142857 repeating. I don't want to deal with that. That's really messy. If I had to add that to anything, I don't want to do that in decimal form. So some of the things that you have to look at are these common denominators, or denominators are easy to get common denominators, right? Some denominators are easier to find common denominators between. Those are cases when fractions are much nicer to work with. Decimals are better to work with when common denominators are not easy to find, or when they maybe don't already have them. Decimals are really nasty to work with when they're repeating. I mean, in terms of working with them, in terms of addition, subtraction, multiplication, division, we don't want to do that. We really don't. You do not want to do that, okay? So those are kind of some of the things to keep in mind. So when you talk about the fact that fractions versus decimals or decimals versus fractions are easier to work with, it really depends on the context. It really depends on what you're working with, okay? Now, if you're rounding, well, then you can do kind of whatever you want, right? And we do that a lot with like money in the store. You know, nobody's in the store saying that loaf of bread costs 5/10 of a dollar. Nobody thinks that way, right? You don't do that with fractions there, but in some sense, it's because most of the time when you're doing that in the store anyway, you're doing some sort of a rounded version of something. So it makes it easy to work with in decimals because you did it on purpose that way. All right.